Our lab. Oh, the first lecture is from Miss Swetashree Acharya, who is currently pursuing PhD under SAR. Hailing from
Would
Cuttack.
you like to do this in the beginning? Because you missed something in the recording.
Okay.
So we can edit it suitably and then put it, okay? So with your introduction, this will get started.
Okay. A very good evening, everyone. Welcome all to the online webinar series on monthly research article spotlight. Now, this is the first lecture by the Miss Swetashree Acharya. She is doing the PhD under Professor T. Pradeep, hailing from the Cuttack, Odisha. She has completed her undergraduate and post-graduation from the Ravindran University, Cuttack, Odisha. Her research focus on the studying the reactions of nanoparticle and nanocluster using advanced mass spectrometric techniques. She joined this lab in 2019 and upgraded to the PMRF in 2021. So she will present her first recent article published in JPCC. So this is the floor to you, Swetashree. Welcome. Please share your screen. Let me.
Thank you, Deepak, for the introduction.
My only request to all of you is that this is supposed to be enriching the student with deeper understanding. Make sure that you ask appropriate questions, penetrating questions, and make sure that you get the right answers. Thank you.
Yeah, is my screen visible?
Yes, it's visible.
Thank you. I welcome you all to this monthly webinar on the paper presentation that we have published recently. This paper is published in JPCC on January 7, 2025, which is titled as Stable Dimer Intermediates During Intercluster Reactions of Atomically Precise Nanoclusters. We all know about what are atomically precise nanoclusters. These are the aggregates of atoms held together in solution by some stabilizing agents such as ligands, having size of 1 nanometer to 3 nanometer. These have transistored packing structure, strong quantum size effect, discrete energy levels, and intermediate chemical and physical properties than the molecules and nanoparticles. These nanoclusters have different active sites through which it can interact with different entities. Some of the active sites which are present in a nanocluster is the outermost is the ligand shell. Then comes in between comes the metal ligand interface. And finally, in the core, there is the a metal core in which we can see the interaction which a nanocluster have with other molecules. Nanoclusters can interact with different ligands, nanoparticles, cyclodextrins, crown ether, fullerenes, cucurbitils, and other nanoclusters to form different cluster assembled materials. Today, we will be discussing about one such interaction that are intercluster reactions, which happen between two nanoclusters. These intercluster reactions are first reported in JACS in 2016, where one PET protected gold cluster and a FTP protected silver cluster has been reacted, in which spontaneous exchange between the ligands and metal atoms has been observed. This reaction is studied with the help of UV visible spectroscopy and mass spectrometry to observe the metal ligand exchanges. Here, with the help of mass spectrometry, we can precisely observe the exchange of each metal and ligand exchanges between the two nanoclusters. In the next Another report on this intercluster reaction was reported, in which a PDT protected Ag25 cluster is reacted with a DMBT protected Ag25 cluster. These two clusters are structurally analogous to each other, where we have seen the spontaneous exchange of metals are observed, forming bimetallic clusters. And these reactions are believed to be proceeding through a a transient dimer, which is observed in the first few minutes of the reaction in the mass spectrometry measurements. People have also synthesized trimetallic nanoclusters using these intercluster reactions. Then we have also done intercluster reaction between two isotopically pure Ag25 clusters, that is synthesized with 107 silver and 109 silver, which shows immediate exchange of isotopes between the two nanoclusters, for giving us the naturally abundant silver cluster within minutes of the cluster isotopically pure cluster getting mixed. But the similar reaction, when performed with a bidentate protected Ag29 nanocluster, this reaction takes a longer time to reach equilibrium, that is up to 3 to 4 hours from the start of the reaction. So we thought of reacting two silver nanoclusters, one of which is centrally doped, that is MAG24 DMBT18 cluster with AG29 BDT12 cluster. We believe that the BDT protected clusters usually don't show any ligand exchanges. So we thought of observing what kind of reactivity this reaction can show. We have doped this Ag25 cluster with gold, platinum, and palladium, and observed what kind of reaction reactivity this reaction has shown. In this 4 reactions, along with the presence of both the parent nanocluster, we have observed a series of 3- charge state species in the range of 3100 to 3400 mass range, which corresponds to the dimeric species generated with both the parent clusters. In A, we have shown the reaction mixture, the full range mass spectrum for the reaction mixture of all the 4 reactions. In B, we have shown the zoomed in mass spectrum for the reaction mixture, where we can see the dimeric species formed. And in C, we have shown the isotopic distribution of the highest intense dimeric species observed in each of these reactions. Then we wanted to check the stability of the dimer formed. So we have monitored the reaction mixture with UV visible spectroscopy, and we have seen the immediate mixture of both the nanocluster shows the UV features for both the parent nanocluster, and the nanocluster features remain stable up to 48 hours, and after that the nanocluster feature for both the nanoclusters start degrading. We have also monitored this reaction mixture with the help of mass spectrometry, where we have seen the presence of these dimeric species up to 48 hours. Then to understand this dimer structure in greater detail, we have done fragmentation studies on each of these highest intense peak observed in each of the reactions. All the 4 dimeric species with silver, gold, platinum, and palladium doped dimers we observed similar fragmentation pattern. I have shown two of the fragmentation processes here with a gold doped dimer and platinum doped dimer. But all the other dimers are also showing the similar fragmentation patterns. So we have shown the generalized schematic for the fragmentation pattern here. What happens in this fragmentation pattern is when we trap the dimeric species and start applying more and more collision energy to it, it first fragments silver DMBT2 fragments from the surface of the dimer, which comes in the lower range, and a series of 2- species is generated in the higher mass range than the 3- species dimer. With application of more collision energy, it generates Ag31, Ag30, and Ag29 species in the 2- charge state. And again, after applying more collision energy, in 50 to 60 collision energy, it regenerates the Ag29 nanocluster. So what information we get from this fragmentation pattern is that both the nanoclusters were the Ag29 remain intact during this fragmentation process, and only the Ag-DMBT fragments are lost during this fragmentation process. Then we have compared the intensity of the fragments, intensity of the dimer, how it varies during the fragmentation process, and compared the generation of the Ag29 nanocluster during the same fragmentation process, where we have observed in case of fragmentation of gold doped dimer and platinum doped dimer, the regenerated Ag29 intensity is more. We have also compared the fragmentation pattern of the dimer with both of its parent nanocluster. In A, we have shown the fragmentation pattern for Ag29 nanocluster. In B, we have shown the fragmentation pattern for the Ag25 nanocluster. And in C, we have shown the fragmentation pattern for the Ag53 dimer. Then here we can see the Ag29 when we fragment, it gives fragment for Ag24 in 2- and Ag22 in 1- charge state species, and then at 40 collision energy, the Ag29 cluster fully fragments, and then it fragments to give all different silver, sulfur, and benzene ring losses. Similarly, when we fragment Ag25, it doesn't get fragment up to 40-50 collision energy, and then it starts fragmenting, losing Ag3L3 unit, and subsequently silver ligand fragment. Subsequently, silver ligand fragments generated from the lower mass. Then, but in the dimer, the dimer fragmentation pattern is entirely different from this two. When we compared the fragmentation pattern with the palladium and platinum doped parent nanocluster, that was showing similar fragmentation pattern with the dimers. That is, the parent platinum and palladium doped nanoclusters also fragments to give 1- charge state species in the higher mass, and silver X ligand X+1 species in the lower mass range. By taking all this experimental observation into account, we have optimized the dimer structure using DFT. The most intense species observed for the Ag53 nanocluster is observed with a silver and 2 DMBT ligand loss from the Ag25 nanocluster. So we have seen that different kind of Ag-DMBT2 nanoclusters are present on the Ag25 surface. The two types are where both the ligands are arranged in a cis fashion, and where both the ligands are arranged in a trans fashion. So we remove both kind of the AGL2 units from the surface of Ag25 and tried to optimize the structure. Although the trans AGL2 unit removed from the surface of Ag25, the final structure showed slightly lower energy, but the structure didn't converge and form any covalent bonding between them. So what we did, we removed the AGL2 unit. So we removed the AGL2 unit in which the two sulfurs are near to each other, and we connected the surface sulfur atoms from the Ag29 nanocluster in this position, and we optimized the structure, and we got the dimer structure for all the dimeric species that we have observed. The stability also comes from the surface CH pi interactions present between the benzene rings on the surface of the cluster. And also from the DFT calculations, we have seen that the gold doped dimer is more stable than the silver doped dimer. Similarly, the platinum doped dimer is more stable than the palladium doped dimer. We have also done reverse reactions. We have also done some reverse reaction in this kind of reaction, where we have done doped gold to the Ag29 nanocluster and reacted it with Ag25 nanocluster. In that case also, we have seen similar dimeric species generated observed in the mass spectrometry. So these are all the reaction that we have performed. We have reacted Ag29 with Ag25. We have doped the center of Ag25 with different metals, gold, palladium, and platinum, and reacted it with Ag29. Then we have also varied the central atom of Ag29 with gold, platinum, and palladium, and reacted it with Ag25 nanocluster. And we have also done reaction where both the clusters were centrally doped with gold and did the reaction. In all the cases, we have observed this dimer formation. So in conclusion, we have seen the stable dimer formation up to formation, and which is stable up to 48 hours. These dimers exhibited superatomic behavior with 16 valence electrons, enhancing their stability. This study revealed the importance of cluster interface in the stability of the dimer formed, and the stability arises due to the interplay of dithiol and monothiol ligands. Thank you. I thank all of you for joining and listening.
Thank you, Swetashree, for this insightful lecture. So this floor is now open for the critical question and discussion. Please, if anyone have a question, ask her. So first, I will go since I have some question. So this mass spec you are doing in the acetonitrile solution. Am I correct?
Yes.
Is there any role of the dimer formation in this acetonitrile solution, or is it forming in some other solvent also?
I have done this reaction in acetonitrile, and also I have previously I have done this reaction in DCM acetonitrile mixture, and in both the cases I have observed the dimer formation, but
Okay.
the impact of
Is
other
solvent any
solvents we have
playing,
not
is
studied.
solvent playing any role during the dimer formation or not?
Um, of, this reactions are happening in solution. Obviously, like solvents will be having some role.
Okay, so this during the mass spec, your molecule is getting ionized, and then during the mass spec, so you're saying there is a CH pi interaction. It's from the only computational or some uh, how
Only
in
in optimized structure, we are seeing that CH pi interactions will be there on the surface of both the nanoclusters.
so the dimer is forming because of the CH pi interaction, or there is other kind of interaction. CH pi interaction is will be very small. So these two big group, how coming to close
I'm
to?
not able to hear you properly.
I'm audible?
Your yes.
I'm saying like this CH pi interactions are very small compared to the size of the, if you are seeing the energy and size of the big cluster. So how they are binding together, making a dimer? Is there any covalent bond formation which I miss or?
Uh,
There is
with our optimized structure, we have seen that there is some covalent bonding
Okay,
between the
yeah,
two
yes,
nanoclusters,
yes. Mm.
and also the stability comes from the CH pi interactions.
So just one question, like when you are doing the mass spec, how you are trapping this dimer, like by providing some particular energy, or like how you trap that dimer?
Uh, This is by mass selecting the dimeric species in the quadrupole. I can
Have
explain
you
that.
observed even bigger mass like trimer, tetramer, anything, even in a small quantity or not?
No,
Oh,
we have not observed any trimer, tetramer, or
okay, so I'm done. If anyone have, please ask.
Swetashree, I have a question.
okay.
Yeah, so this Ag25 is a negatively charged cluster, and so there will be an associated cation also, that is the PPH4 plus some cation. So in your solution, there will be some amount of cation also. So during that reaction and this dimer formation, will it having some interference in this, because all you have is some CH pi interactions. So that can also have some interference. So in the positive side of the mass spectrum, are you seeing some peaks or anything? So something related that.
Um, the positively charged cations will be there in the solution, but we have not observed any its effect in the like with the dimer. We have not observed any
No adducts you have.
positive, yeah, but we have to check the positive mode. Like I have recorded it, but in positive mode we have not seen any change. So
Okay,
we have to look into it.
okay, I'm done.
show one thing just for the sake of curiosity. So this DFT was done in gaseous state, I guess. This DFT calculation.
Yes,
Solvent interference. Yeah.
no, only
Okay.
two cluster
Okay.
were
So
considered.
so the energy what you are getting from even different alloy clusters like gold, platinum, and palladium, they have more or less the same energy. Some only point something is difference except the platinum. So
Yes.
the system is calculated in gas phase, but what do you think that they are getting the energy more or less close to these different atoms, that energy can be changed or anything like this? Any comment? Like palladium, gold, and platinum, This gold and palladium both have more or less same, like only 5 point some electron volt. So you are not getting even central atom exchange also.
Like from DFT, we only we can only from the energy optimization, we can only say that this gold doped dimer is more stable than the silver doped, not
Okay.
silver doped, like this without doping what dimer we are observing, and the platinum one is more stable than the palladium one.
Okay.
Apart from that,
And there is no pi-pi interaction also for stabilization. CH pi is only
only
written.
CH pi is there.
No pi-pi.
No
Okay.
pi interaction.
Okay.
Shweta, it's Amog here.
Hmm.
Are you able to hear me?
Yes.
So this CH pi interaction, is it strong enough in the mass spec during your ionization? Would it not break off because this is a very weak interaction? So would it not break off and form the monomeric parts? Have you compared the energies of this ionization and the bond formation? I mean the CH pi bond energy.
In mass spec, what we are seeing in for palladium and platinum doped dimers, we are seeing the full dimer. This AG25 cluster is having a total of 25 metal atoms, and similarly, the AG29 in AG29 we have 29 metal atoms. So the full dimer, which will be formed with 54 metal atoms, should be there. So that we are observing in
Yes.
case of palladium and platinum. But
Yes, but my question actually is this dimers are forming and are stable in the gas phase of like not harsh, soft ionization condition of the ESI, it is stable. But CH by interaction is quite not that strong. So what if there is other types of interactions occurring in between the clusters and that has some impact? Like Deepak was also telling CH by interaction is very weak, right?
this will
So it is surviving in mass spec conditions. So that's what my doubt was. Is there any other interaction?
Actually, Amoga, when you see these two clusters are joined with the sulfur, linkage is there. So that is also covalent interaction or bonding
Okay.
between
Then
two
that is fine.
silver. There is a sulfur which is bridging these two
Okay.
nuclearity.
Yes, I'm
Which I
seeing that
also
now.
missed earlier.
Yes. Okay. Thank you.
Any other question?
In the UV visible spectra, you have shown that up to after 120 hours, the mixed features of the UV visible is just disappearing to some it is showing some single features of only one cluster, right?
Yes.
So in mass spectrometry also, have you seen like this, like up to 120 hours, what is happening?
Yes, like after 48 hours, when I have done the mass spec of the reaction mixture, only one of the cluster was there. The other cluster, only the AG29 cluster was there, but the AG25 cluster was not present in the mass spectrum, and also the dimeric species were also absent.
Sweta, I have one more doubt. After the 48 hours, you are saying your dimer is degrading. So do you think because of the some charge, you need some bigger
That
cation to stabilize?
actually, that is because these solutions were kept in acetonitrile solvent.
Yeah.
So in solvent, when we keep these clusters, it is not stable for long.
But do you think if you will add some different kind of cation, maybe the dimer is not stable with a smaller cation. It need a bigger cation. Sometimes this stability because of the cationic size of the cation or anion influence. So when this dimer, proper dimer is forming, it need a bigger cation or anion. Maybe that's what could be the reason for the degradation in such a short time, 48 hours.
The reason for the degradation here is because of the individual cluster itself. If we keep in solution, it won't be that stable. Like DMF is soluble, remains stable in DMF. Sorry, Ag29 cluster remains stable in DMF. But if we are keeping it in acetonitrile solvent, it won't be stable for days.
Yeah, I understood. But do you think like any other solvent have can stabilize this dimer like more than 48? Have you checked during this reaction or not? Like you use the DCM and acetonitrile, you are telling. So when
Yes.
you compare the DCM and acetonitrile, in which like in both case 48 hours or you see some difference? Because maybe there will be some different solvent which can stabilize even better. My question in that.
Actually, what we have shown here is these dimers are stable species. When we are mixing the two clusters, the dimers are coexisting with the both of the parent nanoclusters in solution. Till the time one of the nanocluster will be present in the solution, this dimer will also be stable in the solution. Once the parent nanocluster is degrading, then we are not observing the dimer also. But we have to think about how we can increase the stability of the dimers.
Okay, thank you.
Hello, Shweta. Hello.
Yes.
Shweta, can you hear me?
Yes.
Actually, I have one doubt regarding the schematic of this fragmentation pattern, right? So once this fragment comes, you are able to observe Ag29 fragment. But like the starting materials with Ag25 is also present, right?
Yes.
So like have you observed it, or like how exactly is the scheme you are trying to explain?
Actually, when we are fragmenting the dimer, we are only seeing the fragments of silver and DMBT from the surface of the from the dimer. Only silver DMBT fragments are observed, and along with it, some smaller like the Ag29 nanocluster fully with some silver DMBT on the surface are observed. Now, the gold doped dimer fragmentation, the lowest species that we have observed here is gold, 52, like this one. Gold, Ag48, ligand 12, and BDT12 and DMBT10, 2 minus. But beyond this, lower gold doped AGDMBT cluster, we have not seen.
This is the same mechanism for non-doped one also, right?
Yes. Like all the dimers are fragmenting in the similar fashion.
So like my doubt is like when you are trying to do the normal CID, like for Ag29, you can see the fragments with a lower collision energy.
Yes.
Compared to Ag25. But then why the Ag29 cluster is intact, but Ag25 is entirely.
Yes. So like we were thinking that the dimer formation has somewhat increased the stability of the Ag29 nanocluster here. So when it is when we only see the fragmentation of Ag29, it fully gets fragment at 40 collision energy. But here here we are observing the Ag29 in 60 collision energy. Obviously, some part of it will also be fragmented, but still we can observe the presence of Ag29 at 60 collision energy. So the dimer formation would have, we can say, either say it has increased the stability of the Ag29. Also, we can think it as the energy what we are providing with collision, with more collision energy, it is getting used in fragmenting the Ag25 part.
You know, Swetashree, there is some bit of an issue with what you just now said. You are colliding with a mass which was some x in the case of parent clusters. So when you made a dimer, the mass is at least 2x, or it's more than that. So as a result, although you are doing this, kinetic energy is the same between the colliding partners. Effectively, the mass, the energy that is transferred to the colliding partner is less in this per atom energy transfer to this dimer is less. So as a result, it is not thermally activated to the same extent as in the case of, this is like a billiard ball hitting an elephant versus hitting an ant. So I'm just comparing these two just to say that you are not really transferring enough energy.
Yes.
That is essentially what is reflected here. It is not necessarily that you are having increased stability. So this will be questioned later on by people if you were to argue like that. Okay, I just wanted to leave that. Danaka, please continue.
Thank you.
Any other question?
It is important that everyone asks questions, but I do not see too many penetrating questions so that she can't answer. That's the most important aspect about this. So Swetashree, let me just come and ask you one. There are can be many questions that one can ask. So you mean to say that in solution, all that you have to do is put some clusters. They're all hitting against each other. They are forming dimers. Whether you are A plus B you are putting or A and A that you are putting. So this is continuously colliding. And atoms are doing all kinds of exchanges, dimers are forming. So eventually everything dissociates or everything finally disappears. Or is this the view that you are having, or you think that there may be collisions happening, but it does not matter? Many collisions are not effective. Some collisions are effective in making atom exchanges, and eventually things degrade. How do you make something stable in this kind of a situation? Everything is destabilizing eventually. You have an interaction and then a small piece goes away and you get stable dimers. Stable dimers are actually not dimers, right? Stable dimers are dimers with minus something lost in some cases. Some others you have original dimers themselves, but eventually all of these disappear and you do not get anything stable. So what is the point in making these clusters, and what is the point in continuing this cluster science? Do you understand my problem?
Yes.
You make something with so much of effort, put that thing there, and after some time it is not there because all these dimers are degraded. You're anyway making dimers. The moment you put one thing more into this, that is again making a dimer, and it is eventually going off. So what kind of future are they? Is there for these dimers? Deepak will be very upset.
No, sir, I'm not upset.
Yeah. But tell me, what do you think, Swetashree?
This thing may not be that stable in solution, but we have not checked like what happens in the solid state of this reaction.
Mm-hmm. No, but in solution, it is not stable.
The individual clusters are stable in its solid form.
That's right.
In
But in the moment you put this in solution, they are colliding against each other. They are
Yes.
forming dimers. They are degrading. Eventually, everything is going off.
Yes. Mm.
So is this the view that you would like to promote? If that is the case, how can you actually make clusters? You keep on stirring for 12 hours, 24 hours, you make some clusters. The moment you purify it and make a solution of 1 milligram per ml, it's all gone. So what's your thought?
The if we can isolate these dimers and make it in solid, then it may remain stable. In solution, it may not be that stable for a longer time, for a longer period.
How do you make them stable? You go somewhere and then ask someone asks for some money. You get some money. You do this science, and this person says that what is the point in investing all that? And you are breaking all these eventually. So how do you make them stable?
But I'm not sure about the answer right now.
Okay, so I have caught you on one thing. Okay, so please think through this. Okay, let me say that how do you make things stable in a generic sense? A solution, if there is something in solution, how do you make that stable? Is this direction? Can't you answer some questions or this question? What would you do? If collisions are the one which reduce stability, what will you do? You reduce collisions, right? What will you do for that?
Pollutants will be reduced at lower concentrations, but
Very good. And
And maybe we can use different cations as
And lower
as a-
temperatures, Swetashree. Lower concentration, lower temperature, whichever reduces the kinetic energy. In solution, the kinetic energy is nothing but related to temperature, diffusion, essentially. So this discussion has just given you this idea that if, from the first question, if everything is dissociating or not, can't you think of giving some logically sound answer so that people will still support the cluster research? Would anybody want to take this thing? This question, I mean. Deepak, what do you say?
She should also study the effect of the solvent and the temperature effect in this area, and she can vary some different kind of metal also, whether this kind of distability is there in the gold also or not. Completely like different kind of metal cluster.
No, Deepak, if you were to get this question, how will you answer?
Yeah, regarding the stability of this cluster, we should focus on the ligand engineering and as well as what you suggested, lowering the temperature and the concentration of the cluster.
Anybody else wants to take this?
Sir, we can separate out the dimeric species from the solution so that it won't have any reacting species around it, like extra clusters or extra ions. So we can separate, maybe it will be more stable.
Your answer has a flaw. Do you see? That's a nice thought, but it has a flaw. That is, clusters are actually a product of reactions, A plus B. You remove B, A plus B, giving you C. You remove C, then what happens? What will Lee Chatelier principle tell you, Samapti?
Yeah. No, I am telling that if A and B clusters is forming the C, so there are also excess A and B. So if we collect the product,
Yeah,
like
if you remove
separate out,
C, what will happen then?
the reaction will move forward.
Yes, more C will form.
Yeah.
Yeah. So this is not going to solve anything. You want to get a cluster stable in solution. But you say that all the clusters are essentially forming dimers. And the dimers are degrading. So you're spending a lot of money to produce nothing.
Sir, I have a thought that dimers are not degrading. I think dimers are again converting into monomers. That
Very good.
medium kind of thing is there. And
Yes.
in that case, the overall cluster is not degrading. The
Yes.
amount of dimers which are present, that is a limited number, that we agree. And it is continuously changing its forms, like monomers converting into monomers, then again forming dimers. That kind of, because of continuous collisions, this thing is happening.
But what she has shown is that what your answer is fantastic. Very nice thought. But what she has shown is that the monomer is disappearing eventually.
That is the question which...
So how will you answer this question, Swetashree? Or, I mean, that is why I was asking this question. This is relevant to everybody. you need to read more into this. Read meaning not just read. Huh? You have to think through this, what you're observing. That's the question I'm asking you. So I'm giving you another thought here. This obviously, like Deepak said, you know, like what was said, Vivek was talking about. This experiment has told us that there are many more things that we don't really understand about what enhances stability, what reduces stability, how this dimer is dissociating. We don't know a whole lot. So there is a need to investigate this further, increase the stability of the interface. The collisions do produce dimers, but then how do you make sure that these collisions are just producing transient dimers, making the system back to the parent clusters? There are already examples in our own research. But then this system that you have investigated, there's far more studies that you need to do. And earlier there was a question that was asked by Subrito. We have not really understood ligands. Sorry, not ligands, solvents. We have not really understood what all the things present in the solution, like oxygen and all that, what would be their influence? What is the counter ion influence? So you could have taken this question in a slightly different direction to say that, well, we have done this much more to be studied. At this point in time, it appears like this, but this may not be the right. Okay, I just leave that thing there and then ask you one more question and then I will stop. So you'd studied reactions, kinetics, all that thing with mass spectrometry. But that is not how traditionally chemical reactions are studied. Nobody looks at reactions with mass spec, generally. If you go to organic chemistry and ask chemical reactions, how do they study this? They study normally such things with NMR. Or some time ago, they used to do this with absorption spectroscopy. This kind of studies are limited. Now, I wanted to know from you as to the questions that are this study are opening up. How do you use other methodologies to study chemical reactions of clusters? What would you look at? Question ends. Your answer, please.
UV visible gives us some information about the change in the core structure or change in the electronic structure of the nanoclusters involved. But other what technique can be used?
Imagine here is a cluster A, a cluster B, two different things are two spheres. They are coming together and forming something. Can you think of other ways by which this can be studied? Can anybody take this? Swetashree, you are welcome to answer, but I am also asking others.
Yeah.
When size changes, is there something that you can do? Oh, Deepak, you are go ahead.
Yeah, like chromatographic separation, size exclusion chromatography, and the DLS can give some information.
Very nice. What else can we do? The careful DLS can give something. So what else?
But that can also only give information about the size changes during a reaction.
Absolutely.
If there is only atom exchange, then we won't get much information from
Absolutely none.
There is
Yes, but
a, like, if you can do the silver, like silver NMR, even though it's very low nuclearity NMR, sorry, high nuclearity NMR, it's low abundance, but if careful analysis of the silver NMR can give from there. Some people do. I have read the paper of the silver
But
NMR.
Deepak, silver NMR would require you lot of samples if you're monitoring a reaction, right?
Yeah, that can be the limitation.
Yeah, we have a silver NMR here as well. I was planning to do, but it requires a lot of sample.
Yeah. Even I planned for the BWEC, the silver 17 and Swetashree when they gave, but it was not observing that time. So that will be the possibility, I'm saying, like if we can get in that way.
Subrata can answer. Can we do SPA of these things are by our monitoring of through SPA? Can we do that?
Yeah, for SP you need more or less at least 70-80% clean sample. But these all are mixtures. So apart from microscopy, so you should at least that I have told 70% or 60%. But here so many peaks are there. So means it should be a little bit difficult, but can we try it? I can't say that it
Like
is not possible, but can be
like we
possible.
concentrate on the larger particles which we can see, and can we reconstruct that?
Yeah, that can be possible. But if you see that is, if you take only two, one is 29, 31, something like 48. So there are
This is
not
a
so
fragmentation
frag
pattern.
yeah,
Not
but
fragmentation. I'm telling the
no,
reaction between those
reaction
two.
reaction he's talking about reaction. But that
Yes.
nuclear difference is not too much. Let's say Ag29 and PT Ag28, okay?
Mhm.
Fine. So there should not be that much of change in size. So while doing
Okay.
2D, that will be a difficult, but I feel that that can be possible because platinum has more yes, AU, platinum, yeah. So platinum has more electrons. So based on the different scattering intensity can be possible. Like possibility is there, but I can't
Okay.
say this is fully will be possible, but possibility is there.
Okay,
Okay.
can I answer? Okay,
go ahead.
as a
Yeah.
physical chemistry, so I'll answer like this. We can do several techniques like UV, IR, NMR, but all these techniques cannot give the exact information as a mass spec because this cluster, what I'm saying, is not pretty stable. So other techniques like NMR and XRD, all these techniques, you need a stable things, a stable structure. So you can give all the information, but this mass spec can give you the mass number, which you can predict that this is your cluster, like kind of this. I don't.
But again,
But
Bijesh, that puts a question. If it is not stable, then it would be a transient species and not the final product, right?
that's what we are showing in the mass
So
spec. That's what
yeah,
we are showing in the mass spec.
mass spec you can detect transient species as well.
That's why here we are focusing through the mass spec. We want to see all the transition, all these things. So
No,
that's
final
mass spec.
product, whatever final product is forming, maybe that is a neutral thing, which may not be visible in mass spec. That can
Okay.
also be possible.
So can I just comment something? I don't know this will be right because these are transition species. So can we do some spectroscopy on this, not from apart from UV, because UV will give only peaks. Any other spectroscopy, transient absorption, because all other stuffs. I don't know, like just I'm proposing whether this can tell anything about the dimer and all other stuffs.
Very good. Very good.
Can it be possible? I don't. I feel it will be possible because transient species means we can do some spectroscopy, and in order to SAT's question is why funding will be given. So let's say you have input that this dimer. So we are talking about dimer. Now dimer only we are seeing at the mass spec. Okay, so that means that is a transient species. So can we do some kind of different spectroscopy apart from UV and other things? So that
Uh,
will
I
give.
heard I
Yeah.
heard about the jet microwave and jet infrared spectroscopy.
Yeah,
These two are
all are
techniques.
possible. Yeah,
No,
yeah.
listen. In what they do is they make a reaction in one chamber,
Yeah.
and at suitable times they open it to a vacuum chamber where some of the species will go into the vacuum chamber, and that can be read through IR. So this is what
Yeah.
they have done to differentiate between radical mechanism and quantum mechanical tunneling in organic reactions. So
Okay.
maybe not in our case it is difficult, but something related to that where we can quench the reaction and also put it into a vacuum where it will be stable for a longer time, can do some spectroscopy. Even
Yes,
if we
spectroscopy.
can, if there is a possibility, we can also use X-ray techniques. X-ray techniques are excellent techniques to study all the molecules.
Yeah,
But in lower concentration, it will be difficult. But you have to see if some spectroscopy is there in X-ray techniques.
One more thing I will add, then most of these spectroscopy techniques, what we are talking about UV and all transient absorption, this purity is a major factor. Unless we are isolating these products or any transient species, most of these spectroscopy will give us mixed results. And
No, that would be, that's where IR microwave and X-ray techniques will come, because they can give mixture and we can separate them, phase out the differences through fitting the peaks.
yes, but these mixtures are very complex mixtures. If we
Yes,
do kind of reaction in a IR, it will give n number of peaks, and fitting all these peaks will be a very complex thing. What we
and
really see-
again adding to that, we can include computation and also the new thing which is the ML for reactions. I saw that ML is being used for organic reactions very extensively here. So if we can do that for nanocluster reactions, we can try to get mechanisms for nanocluster reactions fairly easily. But it's a far-fetched idea because nanoclusters are very large molecules.
And also, like there are like thousands or like so many numbers of organic reactions to be studied with ML, but we
No,
don't
that
have
is
that
no.
that many
Nanocluster, one paper has come already, which has used machine learning to predict the nanocluster reaction, how it is proceeding and how nanocluster is forming. That too, gold thiol AU25, I think. I'll share the paper when I see it again. So that has been already published. So maybe everybody's
reaction or
trying that
synthesis.
synthesis. So we have started with synthesis, then we can get some data with like your paper, multiple papers. If they come for reactions, we can get more data and we can use ML.
So the reason why I asked this question was to prompt many thoughts, or trigger many thoughts in the minds of people. One thing, that technique that is, Sinchan, you are coming in, and I will just complete it, and then you can speak.
Sorry.
So there are many other thoughts that you can have, many other techniques. For example, there was a mention of Amog mentioned X-ray. There is a technique called small angle X-ray scattering. So this, of course, looks at the size and shape of particles. Very similar to dynamic light scattering, but far more resolved. Similar thing is possible with neutron scattering. A smaller cluster becoming larger, and their transient changes. But all of these, there is this thought that was said previously that you need to do this measurement. Vivek was saying it takes time. So a technique which is short enough is important. And that is X-ray scattering is such a short technique. The scattering event has to be short, like mass spec event is short. Whereas UV visible spectroscopy, if you take that event is long, NMR is long. So you need to have sufficiently short events to do this. So there are a possible range of techniques that one can have. We have not really looked at this domain. The other thing that is very important that probably people have not mentioned is, well, you are doing these reactions at certain conditions. But another condition like low temperature, you are slowing down. So when things are slowed down, it is possible to understand it in finer, better detail, even with the same techniques, which has not been looked at. The environment, the solvent changes these. All of those ways by which the reaction can be probed, you have not commented on this. Now, I'm going to close this and then other questions can continue. But just by asking these two questions, my intention was to make this thinking, and it prompts people who are interested in looking at their own subject area results in greater detail. As you have seen, we get a lot of data and we are very good at presenting that data. We are not synthesizing the data adequately, thinking through the data. And that is why this was asked. So I stop here. Sinchan, go ahead. And Deepak, you continue this discussion. Yeah, Sinchan.
Okay.
Actually, I am from a completely different field, that is droplets. So regarding that intercluster reactions, as we have seen in couple of years that droplets can really change, alter, and see some a new kind of reaction and properties. So when we go to the bulk phase to the droplet phase, there are a lot of enrichment at the surface and the bulk. So is it worth looking at this kind of reaction? Do you think there may be some certain changes compared to the bulk phase and the droplet phase? Because you're doing mass spectrometry using electrospionization, that is producing droplets, and that can
Yes.
compartmentalization can happen. So things squeeze up in a single room, and they can do a lot of collision, lot of reaction, rotation, everything. It's unknown yet.
Obviously, what I think like droplet reactions are much more faster than solution phase reactions.
Yeah.
So if something we are not observing in the solution phase reactions, we may observe something different when these are done in droplet. But
Because you're doing mass spec, so maybe because entering in the mass spec and before entering in the mass spec, there are apparently two phases, like droplet, bulk phase and the gas phase. But during the ionization, there is a droplet phase. So what you are seeing may be happening in the droplet phase, and we cannot compare it with the bulk. It is a little bit tricky to do and difficult also.
okay, to check that, I have done one experiment which I have not shown here. The probe distance variation, what
Okay,
used
okay.
to be done to check whether if a species have different isomers, like one of the isomer is more stable in the gaseous phase and one of the isomer is more stable in the solution phase. So by doing the probe distance variation, people used to check. People have already seen that when the probe distance is more, then the
Smaller droplets will be
abundance
there.
of the gaseous species increases, and when the probe distance is less, the solution in the solution, what species is more abundance, that intensity is more. So we have also checked our dimer species with varying this probe distance, and the dimer species is found for all the varied probe distance. So what we think is that like this dimer is also forming in the solution, not only in the gas phase.
But the probe distance experiment mainly we do for, separating from the gas phase in the droplet phase, not in the bulk phase. Because bulk, you are transferring to the droplet, it is not
Yes.
now in bulk. So how you can compare between bulk and gas phase? It is only droplet phase. So that is maybe from, I don't know things, so can you explain that?
Maybe the bulk she has studied UV, right? UV has shown some changes.
What you are saying?
See, in here, which reaction phase did you show it as a dimer in the UV?
No, in UV we cannot say any feature
Is
is
it
for the
droplet or not?
dimer. Like what we are seeing is the mixture of features for both the nanoclusters in UV, and that
Yeah,
mixture
but
feature remains stable for 48 hours. What we are seeing,
then
not
Sinchan's question is very highly valid now, because in the droplet anything can happen. So in that, maybe it is forming a covalent bond between the clusters as shown by your theory. And after 48 hours, maybe it is not forming because in acetonitrile, Ag29 is not stable. So the second component is not at all there in the solvent or in the solution. So it is not at all in the droplet also. So that's why dimer is not forming.
So that
That's
problem
a
can be
valid
solved.
question.
What I think that problem can be solved, we can spray at different distances and see what is the UV. So different distances means different droplet size. So that means reaction is something alternation. So we can perform that kind of experiment.
No, again, you are going to droplet, right? We need to see if it is occurring in the bulk, because she's first mixing in the bulk and then talking about the reaction occurring in the bulk with the use of mass spec. Again, you are going to droplet, right? So that can again give you the dimer.
So
That point
my
is a
concern,
good point.
my concern is there, like it is in the
asking
droplet
whether
phase,
this reaction
droplet
can
phase or
happen in
bulk phase. That's my concern.
Yes, Shweta was telling something.
No,
Yeah, tell.
what I understood, Sinchan was asking whether this reaction can happen in the droplet itself,
Yeah, not in the bulk.
not in the bulk.
So you have to have two nozzles to mix them.
Yeah.
Okay,
Like
that
the
can
extractive
also
loop
be tried.
stress.
Yeah. Yeah, they should not be
Extractive loop
mixed
stress.
first. They have
Yeah.
to be two nozzles mixing together, spraying together.
Before mixing them, you separate them and mix in the droplet itself.
Yes, understood.
Then you deposit and take the ink or other characterization.
Yes.
And
Can
also
you
regarding
just
the
explain it again? What you
like
what
you
experiment
have
is
two
that?
electrospray ionizer nozzles. Okay. So you make it at 45 degree each other, and if you spray them, you can come and see that also in TV. We do that. So they are sprayed from different that is the syringes. They're sprayed because they are not mixed previously. You spray them and deposit them and see the.
Okay.
So they are not mixed in the bulk. They are mixed in the droplet.
I just saw in the internet, there are multiple papers with machine learning for nanocluster. Even the intercluster reactions have been studied by Professor Hanu's group. So people can go through those papers. I can talk here if we can try this with nanocluster as well.
Okay, this is time to end. Thank you so much, Swetashree and others for this engageful discussion. So we will meet again next month with another speaker, Mr. Amog Varsa. So he will discuss about his recent publication. So thank you so much, everyone, once again. Bye for time.